Okay, so last time we started talking about chapter 8, and in chapter 8, we talked about some important sort of conversions that we do use in chemistry. We talked about the idea of a mole. And remember that a mole is abbreviated as MOL. And we do use a mole as sort of a representation of a certain amount of something, again, like a pair is 2 or a dozen is 12. In chemistry, 1 mole of anything basically will equal Avogadro's number, which is 6.022 times 10 to the 23. This is Avogadro's number. And remember, though, that with Avogadro's number, the units do sort of change or can change. Just like I said, we had a dozen roses or a dozen donuts, they both represent 12, but they are different things. So sometimes, in most cases, these are really the 2 common units that we will use with Avogadro's number. Atoms are molecules, but they really could be anything. And we really can use this as a conversion factor to go between moles to atoms or moles to molecules or backwards. And we could write basically 2 conversion factors, 1 mole over Avogadro's number here, or Avogadro's number over 1 mole. And again, depending on what you're doing, you could use either one of these sort of guys as a conversion factor. Probably a more, say, useful-ish type of conversion factor that we do use a lot is molar mass. And molar mass does come from the periodic table. So when we calculate something like molar mass, it has units of grams per mole. So those are always sort of the units associated with molar mass. And we do get a number for molar mass, and the number is always basically how many grams there are. And it's always really 1 mole. So the moles part is always 1. And obviously the number that you get is how many grams. It really does come from the periodic table. So we talked also about atomic mass last time, but you could go to the periodic table and pull that bottom number there. And that bottom number can be the molar mass, which for carbon here would represent that there are 12.01 grams per mole of carbon. Which means you again could write 2 conversion factors, 12.01 grams over a mole of carbon, or a mole of carbon is 12.01 grams here. We also can apply sort of molar mass to, molecules as well. So if you have something that's a molecule, you basically just add up all the parts to it. So if you had something like C2H4, we would go to the periodic table. We have carbon. We would also look up hydrogen there and see the number on the bottom. And basically, we would just add all the parts together. So there are 2 carbons, each at 12.01 grams per mole. There are 4 hydrogens, each at 1.008 grams per mole. And if we do all that good stuff there for this example, looks like we end up with 2805 grams per mole would be the molar mass of this guy. Once again, we can basically use it as a conversion factor. So molar mass is really important. We use it a lot in chemistry. And again, it is really the conversion factor to go from grams to moles or backwards as well. So that is definitely what you want to use whenever you have basically those units and you need to go from one of those units to the other. Periodic table, molar mass as your conversion factor. Any questions on any of that stuff there that we talked about last time? Yeah. So say one more time, the question asked to find. It would probably, if they just gave you a formula and that's all they gave you, then that would probably be the molar mass they're asking about. So you could have something where you would need to find the mass, like like what we did in lab, for example, empty crucible, then you put like oxygen on at the end or something like that, you subtract the two, and that would get you the mass of the oxygen. So it could be both, but if it's probably just the formula, they probably are talking maybe about molar mass. So, but they usually will specify molar mass as to what you want. So, other questions? So we did some examples last time, so let's do some more here. So why don't we try here zinc? Want to know how many grams there are in 0.256 moles of zinc. Zinc is 6539 on the periodic table. Take a moment and see what you get. Okay, let's take a look. So in this case, we are looking for grams. We have moles given to us. So this is a grams to moles conversion. And that again is the molar mass from the periodic table, which again, we could get from right there. So again, that number means that for zinc, there are 65.39 grams per mole of zinc. And that is the molar mass. We could also, again, use it as a conversion factor and flip it around if we needed to. A mole of zinc would be 65.39 grams. Again, if you were just asked what is the molar mass of zinc, you could just write 6539 grams per mole would be an acceptable way to write that. But again, we could kind of turn those into conversion factors to use. And in this case, we could take a dimensional analysis approach. 0.256 moles of zinc is what we're starting with. So remember, in dimensional analysis, its opposites cancel. So to cancel, we will roll with this guy here so that the moles end up on the bottom. The moles of zinc here will cancel, and we will end up with 0.256 times 6539. Looks like 16.7 grams of zinc in this case. Sig figs off of that original number there in the box. Any questions on that conversion there? Again, here we did not need to use Avogadro's number because there was no mention of atoms, molecules, or anything like that. So as we talked about, I think the other day, you don't want to use Avogadro's number everywhere. Sometimes people have the tendency to always want to kind of put it into the calculation, but you don't need to do that unless there's anything about atoms, molecules, and stuff like that. Any questions on that there? All right, let's try a few more here. Let's try both of these. How many moles and then how many molecules in our guy of ethanol? A couple of numbers be helpful. Carbon from the periodic table, 1201. Hydrogen from the periodic table, 1.008. And with really grams here. And in the first question, we do want to go to moles. And then really, since we're starting with the same grams of both, it's the continuation. We want to then go to molecules. So remember, sort of our pathway to do that, grams to moles is the molar mass, right? That allows us to do that from the periodic table. And to go from moles to molecules, here we do have molecules mentioned in the second part of the problem. So that definitely is Avogadro's number needs to be used at that point. So go from moles to molecules, we need to do Avogadro's number. So we'll do the first part here first, which means we do need to get the molar mass of ethanol. So again, we're just going to add up all the parts from the periodic table. So our molar mass here of ethanol would be, there are 2 carbons, each at 12.01 grams per mole. There are 6 hydrogens, each at 1.008 grams per mole. And there is just 1 oxygen at 16 grams per mole. So again, this is our carbon, that's our hydrogen, and that is our oxygen from the periodic table. So if we do all that good stuff there, 12 times 12.01 plus a 6 times 1.008 and a 16 gets us about 4607. 46.07 grams per mole would be the molar mass there of our ethanol. Again, we're going to use that as a conversion factor. So we'll start here with 3.2 grams of ethanol, C2H6O. Once again, doing a dimensional analysis setup here, we're going to go opposites with the grams. So the grams are up on top. We need to put them on the bottom, which is essentially dividing by the molar mass is what we're doing. So we'll go with the 46.07 grams on the bottom and a mole of our ethanol there on top. The grams here will cancel, and we get, if we get an answer here, which we're looking for 46.07, we would end up with something like 0.504 moles of ethanol here. Any question on that first part of the calculation there? At this point, we're just really going to continue on with the same number because it's basically the same grams of both parts, so it's the same moles. At this point, this is where we will use Avogadro's number. So continuing on with our calculation here, we know that we need to use Avogadro's number, which is 1 mole, in this case, of C2H6O would equal 6.022 times 10 to the 23. And these would be molecules, as that is a molecule. So that is the units that we would use here. And we will continue on with our number here. We'll use our rounded number here, 0.504 moles of C2H6O. Once again, setting it up dimensional analysis way where our moles will cancel. We need to put moles on the bottom. So 1 mole of C2H6O. Up on top is going to go Avogadro's number. And that would be molecules. The moles will cancel. We do want to make sure that we use our exponent button as when we punch that Avogadro's number in. And it looks like we'll end up with something like 3.03 times 10 to the 23. And again, these would be molecules of our C2H6O. Any questions on that part? Yeah. So remember, part of what they want you to do in this class and continue on with the rest of so your chemistry career is they want you to show your calculations like this, if that's what you're asking, with dimensional analysis. So anywhere where you could show a calculation with dimensional analysis and the units canceling is really how they want you to kind of do that. I think we talked about it at the very beginning of the class, right? They kind of want you guys to kind of do that so that when you go into 1A and 1B that, you know, you kind of do your calculations like that rather than just sort of taking a number and multiplying by another number with no units. So they're really big and really pushing to make sure that you do set them up like that. So you do want to do it that way. Yeah. So in most cases and most calculations that we do, you could kind of set it up in that dimensional analysis approach, and that's really sort of the approach that you could do. There are a couple where you can plug and chug into a formula. You don't have to necessarily do it like that, but most of the time when you can do it, you want to do it. Other questions? Okay. So let's try another one here. What is the mass in grams of a molecule of caffeine? These are some of our same numbers here. So carbon is still 1201, hydrogen 1.008. Nitrogen 1401, and our oxygen here 16. Okay, so looking at this one, we're looking for grams. We do see the word molecules. So again, that tells us Avogadro's number needs to be used here. So our pathway here is we're actually starting with molecules in this case. We need to go to moles, and again, it'll be Avogadro's number that will allow you to do that. And from moles, we then will go to grams using the molar mass, again, from the periodic table to do so. So in this case, we could actually start with the first part here. We have 1 molecule of our caffeine here. So 1 molecule of our C8H10N4O2. And in this case, we're going to use Avogadro's number to go from molecules to moles. That means that moles will go up on top and Avogadro's number will go on the bottom, 6.022 times 10 to the 23 molecules here. The molecules will cancel. If we stop our calculation right at this point, we are right there at moles. So we do need to get the molar mass there to finish the calculation. If you want to get a number, you can, just don't round too much, but we'll continue on with it in one calculation here. So in this case, we have 8 carbons at 12.01 each. Carbons We then have 10 hydrogens at 1.008 each from the periodic table. We got 4 nitrogens at 14.01 each from the periodic table. And lastly, there we got a couple of oxygens, each at 16 grams per mole. That's a big molar mass there. So I think we'll take a look here. That plus 10, 1.008 plus 4 times 1401 and 832. About 195. Does that sound right there? About 195 grams per mole. Double check real quick here. Actually, 194.2 sounds better, I think, right? There you go. 194.2 grams per mole. That more what you got? Yes, I hope. Yes. All right, so go with 194.2. We're going to use that as our conversion factor here. And in this case, we want moles on the bottom. So we're going to go with moles on the bottom of this giant thing here. And 194.2 grams there on top. We're going to multiply basically across the top there, which is really just the molar mass. So nothing really much to multiply. We're then going to come back here and divide by what's on the bottom, which is Avogadro's number, making sure that, again, we do use our exponent button to do so. And so we're going to take that and divide it by 6.022 to the 23rd. And that will get us basically 3.225 times 10 to the minus 22 grams of our caffeine here. Any questions on that one there? Yeah. Yeah, so in this case, it's kind of I won't say unusual case, but kind of a case where really this number here is kind of like the only number that was given in the problem. The rest of these are really more like exact numbers. And so is technically one. One would be a number that you would probably count, right? If you had one of whatever it is there, it would be something to count. So you can actually give as many sig figs you want in this case. I went to 4 because of the molar mass was the 4. So that's why I did that. But you could actually give it any number of sig figs in this case, because it would probably be a thing that would technically be counted, like an exact number. Yeah, any type of problem where, it's kind of like, you have one molecule, it's kind of like you have one apple or, one pen or something like that. There would be all things that would really be something that's counted. And that's really the second definition of something that's an exact number. It's either an exact number is something that's like a definition, like 1 inch is 2.54 centimeters, or is something that's counted. So in this case, you would assume, if you just had like one atom, you would just kind of count it. Yeah. Other questions on that? Okay. So one last thing here that we're going to look at is, let's say we had something like we wanted to know how many hydrogen atoms are there in 42.5 grams of C2H4. So if we had a problem like this, we're actually interested in just the hydrogen part. We're actually not interested in the entire formula. So we do need a way to go from kind of like the whole thing to just the hydrogen part in this particular example. And we could actually do that by looking at the formula itself. And the formula itself, when we look at it, as we'll talk about here in just a second as well, these numbers on the bottom can represent the moles of each of those elements that are present. So from an actual chemical formula, you could actually come up with some conversion factors that you could use. So for example, if we look at this one, for every 2 moles of carbon that there is, there are 2 moles of carbon for every 1 mole of the entire thing. There's also 4 moles of hydrogen for every 1 mole of the entire thing. So we could use the entire formula and basically come up with really kind of like a mole to mole relationship between the whole thing and each individual element. That is going to help us sort of figure out how we could get to just hydrogen here. And that is, we have grams of the whole thing. So in order to use these, we'll still need to convert the grams into moles of the whole thing. So that's where we'll begin. So we'll start by taking the whole thing here and converting it into moles. So we do need to go 2 times 12.01 plus R4 times 1.008 for our hydrogens. And that is going to give us a molar mass of we saw earlier, I think 2805. So the first thing that we would want to do is take the grams of the whole thing and convert them into moles, just like a normal sort of molar mass calculation. And again, here grams will go on the bottom so that they cancel. And if I stop my calculation right at this point, I would be in moles of the entire thing. And that's really what I need to use my conversion factor here, because that is basically moles of the entire thing, gives us basically 4 moles of hydrogen. By the way, again, the 4 is just the subscript that we see here in each of those cases. So using that conversion factor from the actual chemical formula, that's going to allow us to go from the whole thing, which in 1 mole of the entire thing, there is 4 moles of hydrogen. So at this point, we use the formula to do that conversion, and that's going to allow us to go to just the hydrogen by itself. Am I done here with the calculation at this point? I'm in units of moles of hydrogen, but I do want atoms of hydrogen, which means to finish up this calculation, I need to use what? Yeah, we do need to use Avogadro's number here. So we would use our final part of the calculation using Avogadro's number. And that would mean that 1 mole of hydrogen would be 6.022 times 10 to the 23 atoms. The moles of hydrogen would cancel. We're going to multiply everything on top together. So 42.5 times 4 times Avogadro's number using our exponent button. We're going to hit equals, and then we're going to divide by what's on the bottom, which is basically 2805. And that would get us about 3.65 times 10 to the 24 atoms of hydrogen are present in that particular formula. So these are kind of the same conversions we used before. This is our molar mass. That is Avogadro's number. But here, using the chemical formula, we're able to come up with a relationship that allows you to go from the whole thing to just one of the elements that are present. Any questions on that there? Now, at the end here, if I didn't want atoms, but I wanted how many grams of hydrogen that would be, instead of using Avogadro's number at the end, I would use the molar mass for hydrogen at the end, and I could get how many grams. So there are obviously a couple different ways you could have ended this one. In this case, we were looking for atoms, but again, if we did molar mass here, that would tell us obviously how many grams of hydrogen there would be in that particular guy. Any questions on that there? Question on grams, moles, molar mass, Avogadro's number. All right, so let us then continue on. We're now going to talk about some formulas and how to calculate empirical formulas and molecular formulas. As we talked about, a molecule is really a combination of 2 or more atoms. Remember, a molecule can be 2 or more atoms that are the same element, or 2 or more atoms that are different elements. A chemical formula, as we talked about, really does express basically how many of those atoms are present. And the molecular formula tells you exactly, really, how many atoms of those elements are present. So the molecular formula, when you do see it, is really the formula that tells you exactly each element, how much is really there. And that's a little bit different than the empirical formula, which tells you sort of the simplest whole number ratio, what's present. So molecular formula shows you the exact amount that's there. The simplest type of molecular formulas is our diatomic molecules, like our H2 or O2 or N2. In sort of their simplest forms, molecular formulas are written by grouping atoms together, like we just saw there, C2H6O. Reminder that the subscript that we do see always goes to the guy to the left. And if there's nothing written there, it is assumed to be 1, right? So always goes to the guy to the left, and nothing there is 1. Now, molecular formulas can be written in a couple of different ways. Sometimes they really just give you the basic sort of what is there. And sometimes formulas will give you sort of how things are set up. So for example, we could also write C2H6O as CH3, CH2OH. And that again is the same 2 carbons, the same 6 hydrogens, and the 1 oxygen. This molecular formula gives you a little bit more information about how this thing is actually connected together. It is actually connected together like so. And again, if you sort of break it up there, you can see that is CH3, CH3. That is CH2, CH2, and over here, OH, OH. So this sort of molecular formula gives you a little bit more information about structurally how they are hooked together. Not all formulas will do that. A lot of times formulas are just written like the top here, where it's just like this is what's there. So you should be aware of that, because sometimes you see different formulas written on things and they are the same thing. And sometimes people think they're actually different things. Yeah. They both would be molecular formulas. Sometimes people will call this one more of a structural molecular formula, because it kind of gives you some information about the structure and stuff like that. Both are considered molecular formulas. Yes. Yes, sir.
Also write as H5OH because you don't want the structural effect.
Yep. Now, another type of formula which is really important is the empirical formula. And the empirical formula is the simplest whole number ratio that's present. So the empirical formula may not necessarily give you actually how many numbers of each of those elements are present in the actual compound, but it is really the simplest ratio of what's present. So for example, H2O2, which is hydrogen peroxide, has 2 hydrogens for every 2 oxygens that's present. That is really the same thing as 1 hydrogen for every 1 oxygen, which means you could reduce this down to the empirical formula of HO, and that would be the empirical formula here. The one that we just were doing a second ago, C2H4, that is basically 2 carbons for every 2 hydrogens, or 4 hydrogens, so they're there. And we could divide everybody by 2, still get a whole number, and you would get 1 carbon for every 2 hydrogens, which means the empirical formula here would be CH2. So if you could take a formula, for example, and you are trying to find the empirical formula for it, and you could reduce down all the subscripts by a whole number, divide everybody out by a whole number, and you get a whole number, then that would be your empirical formula. There are some formulas that the empirical formula and the molecular formula are the same. So for example, water is 2 hydrogens for every 1 oxygen. And obviously you cannot reduce that down any further. So H2O would be both the molecular formula and the empirical formula. So sometimes they are the same formula. Most ionic compounds, actually all ionic compounds, their formulas for ionic compounds are always empirical formulas. And that's because when we take an ionic compound, which is a positive guy and a negative guy, we always put that together to equal 0, the charges in the simplest way possible. And that is why the correct ionic formulas are always empirical formulas. That is why when we take something like sodium and chloride and put it together, we just need one of each. And that is why when we take sodium and chloride, the correct formula is NaCl and not Na2Cl2, even though it's balanced. That needs to be reduced down by 2 to the proper empirical formula. So that is why when we put it together with T equals 0, all ionic compounds always are empirical formulas. Any questions on that? All right, so if we take a look at another one here, N2H4, that's basically 2 hydrogens for every 4 hydrogens. Sorry, 2 nitrogens for every 4 hydrogens. We can reduce that down to 1 nitrogen to 2 hydrogens. We're basically just dividing by 2. Yeah. And that gives us our empirical formula, NH2 here. As I mentioned before, it is really only the molecular formula that tells you exactly what is present. Again, occasionally the empirical formula and the molecular formula, that's the only case where they will sort of tell you that. Empirical formulas are oftentimes used in labs and lab experiments because they're very easy to sort of figure out. Basically a simple experiment like what's on tap for today. You basically just get some masses and convert to moles, and you can figure out the empirical formula really, really simply. So empirical formulas of certain things, as I mentioned, these are some examples, obviously, where they are the same. You cannot reduce down any of these guys here to get a whole number for everybody. Again, you cannot have a subscript that's not a whole number. You can't like have a half a mole of oxygen or half an atom of oxygen. So they all has to be, when you have your subscripts on the bottom here, these numbers, they all has to be whole numbers. All right, so take a second here and write the empirical formula for each of these. We have 2 carbons for every 2 hydrogens, which means you basically could divide every 2, and that would give you basically 1 carbon for every 1 hydrogen would be our empirical formula. In the case of the second one here, that is 2 iodines for every 5 oxygens. There's really no way to divide that down to a smaller number and still have a whole number. So in this case, this would also be the empirical and molecular formula here. And lastly here, glucose, basically 6 carbons to 12 hydrogens to 6 oxygens. Here we could actually take everybody down by 6, divide by 6, and still get whole numbers, which would give us basically 1 carbon, 2 hydrogens, and 1 oxygen would be our empirical formula. So again, you need to kind of lower them down, but they still need to be whole numbers in order for it to be an empirical formula. Any questions on any of those there? Okay. So that's one way you could kind of calculate the empirical formula, just by reducing down the molecular formula, but to whole numbers. So let's talk a little bit about percent composition by mass. Percent composition by mass tells us basically the percentage of each element that's present by mass. We basically find it by taking the mass of the element we are looking for, divided by the mass of the compound, and times it by 100%, basically. So we take the mass of each element, basically the molar mass, divided by the mass of the entire thing, and times it by 100. Kind of similar to what we did with the hydrate the other day. You got the mass of the water part, right? Divided by the mass of the entire hydrate, and you times it by 100. So that is basically what you did there to find the percent composition of water in that hydrate. It's basically the same calculation. So let's take a look at one here. So if we did hydrogen peroxide and we wanted to calculate the percent composition of hydrogen and the percent composition of oxygen, the first thing that we would want to do is get the molar mass of this compound. So from the periodic table, 2 times 1.008 for for our hydrogen, plus 2 times 16 for our oxygen. That is going to give us 3416, I believe, grams per mole. So to find the percentage of hydrogen, we would take the mass of just the hydrogen part, which would be 2 hydrogens, each at 1.008, divided by the molar mass of the entire thing, 34.16, times 100% in this case. So in this case here, we would end up with and then this should be actually 34. Oh, I think I lost an O there, huh? 01, 02, I think. 34.02, I think is what that should be. Getting old, I can't read the calculator anymore. All right, so we're gonna take 2 times 1.008 divided by 34.02. We're gonna times it by 100. If I didn't mess up any numbers here, this should be 5.926% hydrogen by mass. We could do the same thing here for our oxygen. So the percent of oxygen, since there are 2 oxygens in this case, 2 times 16 divided by 34.02 grams per mole times 100%. So that's going to give us 32 divided by 34.02 times 100%. Gives us about 94.06% oxygen. Because these are the only 2 elements, right? This should add up to about 100%. Yes, and they do when you add them together, approximately 100%. May not be perfect, but should be obviously near the 100% mark. This is mostly made up of oxygen by mass, right? So oxygen is 16 grams versus hydrogen, that's 1 gram. So the majority of the mass of this compound is obviously made up of the oxygen. Any questions on that there? Now, what would happen if we did our empirical formula? So why don't you do that? What is the percentage of hydrogen and oxygen in this formula here? And once again, hydrogen 1.008, oxygen 16. So calculate the percentage of hydrogen and the percentage of oxygen. Okay, so let's take a look here. So same approach, we would need the molar mass of just the empirical formula here, which would be 1.008 grams per mole for the hydrogen and 16 for our oxygen. Gonna be 1701 grams per mole, I hope. All right, so in this case, we have just 1 hydrogen, so 1.008 grams per mole up on top, divided by the molar mass of the entire compound, times it by 100%, and that gives us 1.008 by 1701 times 100, 5.926% hydrogen. We could do the same thing for oxygen, which would be 16 grams per mole, since there's just 1 oxygen here, divided by 1701 grams per mole, times it by 100%, and again here, 100, 94.06% oxygen. Are these percentages different than what we saw in the molecular formula? They are exactly the same. So they're exact same percentages. They're exact same percentages because the empirical formula is just the simplest ratio of what's present, which means those elements have the same mass no matter what. So you have the same ratio, you have the same percentage by mass of each of the elements that are present. Any questions on that? By the way, since these were the only 2 elements here, after I got this number, I could have done what to get to this number? Subtract 100, right? 100 minus it would have got us there, since those were the only 2 elements present. So you could have shortcutted it that way if you wanted to, obviously, to get to that number. Any questions on that there? Okay. All right, so why don't you take a second here and calculate the percentage of each of these guys: hydrogen, phosphorus, and oxygen. Hydrogen 1.008, phosphorus 3097, and oxygen still 16, I think. Hasn't changed, hopefully. Okay, let's take a look here. So once again, we're going to start with the molar mass. So we got the whole compound there. So that's going to be our 3 times 1.008 for our hydrogen. We're going to add 3097 there for our phosphorus, and 4 times 16 for our oxygen in this case. That looks like a 97.99 molar mass, 97.99 grams per mole. Any questions on how I got that number there? At this point, we're just going to take our first element there. We'll do hydrogen. So there are 3 in the formula. So 3 times the molar mass of hydrogen from the periodic table divided by 97.99 grams per mole times 100% there. That's going to give us 3 times 1.008 divided by 97.99 and times it by 100. We'll call it 3.086% hydrogen. We'll do phosphorus next. So the percentage of phosphorus would be 3097, since there's just one, divided by 97.99, and also times it by 100% here. And that's going to get us 30.97 divided by 97.99 times 100. 3161, we'll call it 31.61% phosphorus. And lastly, if we worked out the last element here, the percentage of oxygen would be 4 times 16 divided by 97.99, and also again times 100%. That is going to get us 4 times 16 divided by 97.99 times 100%. Looks like 6531% oxygen. Once again, if we just quickly look at it, we hopefully got about 100% when we had all that together. Mostly made up of oxygen, followed by phosphorus in terms of the percent by mass. Any questions on any of those? Yeah. Yeah, again, in this case, since there really was no numbers given to us, really the only numbers we kind of used was the molar mass. So you typically it's 4 significant figures for that. So that's why I went with 4. Yeah. Other questions? So one way to calculate the empirical formula is obviously if you have the molecular formula, you can basically reduce it down by whole numbers. But there is a way to calculate the empirical formula. And there's a few steps to actually calculate an empirical formula. Let's talk about that. So the first thing you want to do, and a lot of times in sort of empirical formula problems, they will actually give you the percent composition by mass of each of the elements. So they'll say, hey, this thing's 30% oxygen, 20% hydrogen, and so forth. So a lot of times you want to take the percent composition that they give you and convert them into grams. And the easy way, right, to convert something into a percentage into a number is to assume that you have 100 of it. So in this case, a lot of times we assume that we have 100 grams of it, because what that essentially does is keep the numbers for the percentages the same numbers for the grams. So that's the way that we kind of do it. Once you have the grams of each element, you then will convert it into moles. And to do that, we use the molar mass from the periodic table that we have been using in our conversions. At this point, you will have the moles of each element that are present. We then, on the third step, divide by the smallest number of moles. So for example, let's say after the second step, we ended up with 2 moles of A and 4 moles of B. So let's just say we got those numbers after the second step. What we would do at this point is we would divide everybody by the smallest number of moles, which in this made up example here is 2. So we would divide this guy by 2. We would divide this guy by 2. And that would equal 1 for the A, and that would equal 2 for B. And if we divide by the smallest number of moles like we just did, and you pretty much hit a whole number, that would be your empirical formula. So our empirical formula here in this example would be AB2, as we did hit whole numbers for each. Now, things don't always work out that great that you hit whole numbers. So if you do not hit a whole number, you do need to sort of figure out a factor to get to a whole number. So let's say we had a different example here where after doing step number 2, we ended up with, say, 2 moles of A and 5 moles of B. In this case, we would still divide by 2. That would give us 1. That would give us 2.5, I think. And that would give us an empirical formula of A, B, 2.5. That is a problem because we cannot have, right, like a half of it, right? So it has to be a whole number. That is too far to round. So when you're doing empirical formula problems, in book problems and textbook problems, you really do not round to the nearest whole number unless it is like almost at that number. Like you ended up with like 1.99 or 1.98, that's pretty close to 2. You could round. Or maybe you ended up at like 2.01 or 2.03, just above the number, you know, that's okay to round. But if you end up when you divide it with like a number that ends in like 0.25, 0.5, 0.33, something like that, that is too far to round. And you need to find a number to sort of fix it with. So in this case, 2.5 would be too far to round to a number. So what we need to do is go, if I take something like 2.5 and I times it by 1, that is obviously 2.5. If I take 2.5 and times it by 2, that gives me a whole number of 5. So what you would want to do is take 2 and times it by the entire empirical formula, not just the guy with the 2.5, but everybody. So you would take that basically and times it by 2, and that will give you the proper empirical formula of A2B5 in this example. So not always will you get a whole number when you do the division. And like I said, if it's not really the whole number because of rounding, you just missed it and it's really, really close, then you can round. But if it's something outside of that, you should not round. You need to find a number. So typical endings where you should not round, like 0.33, 0.5, like I said. And so those are really kind of too far to sort of round. You do need to find a number to do that. Now, something like 0.33, if you times it by 3, would give you like 0.99, which would then put you pretty close to rounding to the next number, whatever the front number would be. So, you know, you can do that. So those are the steps to basically find the empirical formula. Percentages to grams, grams to moles, divide by the smallest number of moles. If you hit whole numbers, that's your empirical formula. If not, you need to find a factor to get yourself to a whole number. Yeah. You probably should show the work that, you know, that you divided out, you didn't get the whole number, and then, you know, kind of what factor that you got it to. Yeah, in this case. Other questions? Okay, so we're going to lay it up there.